Hey everyone and welcome. In this video we are diving into an important concept in modern performance critical programming, data-oriented design or DOD, and how it applies to C++. This isn't just a buzzword, it's a mindset shift that's been critical in systems like game engines, simulations and real-time applications. So let's explore what it is, why it matters, and how you can start applying it in your own C++ code. So what is data-oriented design? Traditionally, in object-oriented programming, we think about organizing code around real-world objects. We build hierarchies with inheritance, virtual methods, and polymorphism. That works well for modeling behavior. But what if the behavior isn't the bottleneck? What if data access is? That's where data-oriented design comes in. DOD is all about organizing data for how it's used, not how it looks conceptually. It's about understanding how the CPU works, especially the cache, and designing your data structures to take advantage of it. Let's break this down with a simple example. Imagine this C++ class. And let's say we have a vector of enemies that stores 10,000 of these. Now suppose every frame we loop over this vector to update positions based on velocity on every frame. That might look like this. Looks fine, right? Well, from a performance perspective, it's okay. But there is a problem here that DOD addresses directly. The CPU cache. Modern CPUs are fast, but memory is slow. To speed things up, processors use cache lines, small chunks of memory loaded into the CPU. When data is contiguous and frequently accessed, the cache helps a lot. In our example, each enemy object has 5 or 6 variables, but we only use 4 of them during the position update. So for every enemy, we are pulling the whole struct into the cache, including health and isolive, which are not needed for movement. Multiply that overhead by thousands of objects, and you start wasting cache space and memory bandwidth. DOD solves this by separating data based on how it's used. Let's refactor this with DOD in mind. Instead of a vector of structs, we use separate arrays for each component. Now, when we update movement like this, we are only accessing the data we need, and it's tightly packed. This means fewer cache misses, more efficient use of memory, and faster execution. This isn't just theory, it can be orders of magnitude faster, especially at scale. So why does this matter in C++ specifically? Because C++ gives you direct control over memory layout. Unlike many higher level languages, you can choose exactly how and where data is stored. That's a superpower. And with great power comes the need to use it well. Data-oriented design aligns beautifully with C++ features like stud vector for tightly packed arrays, manual memory management when needed, SIMD optimizations, and cache-aware design. You can even go further with things like entity component systems, which are common architecture in game engines using DOD principles. So how do you know when to apply DOD? Not every program needs it. If you are building a GUI app or something, depending on input-output, DOD won't change much. But in real-time systems, games, physics simulations, high-frequency trading, or even signal processing, data layout becomes a primary performance factor. Here are some signs DOD might help. You have large collections of data-heavy objects. You are iterating over them in tight loops. Performance profiling shows memory stalls or cache misses. Most of your CPU time is spent reading or modifying object state. If that sounds like your use case, DOD is worth a look. Let's talk trade-offs. Data-oriented design isn't free. It can make code less intuitive, especially at first. For example, in object-oriented programming, we might write this. But in a data-oriented design system, damage might be processed in a batch across arrays. That's more verbose and less encapsulated. Also, DOD tends to favor data pipelines over object hierarchies. If your team is used to traditional object-oriented programming, it can be a mental shift. You may end up writing more boilerplate and organizing systems around access patterns rather than domain logic. But if performance matters, really matters, the gains are worth it. You don't need to refactor your whole code base. Start small. Identify a tight loop in your game or simulation. Use a profiler. Look for hotspots. Then try separating your data, just that one part, into a structure of arrays. Then run the profile again. You will probably see measurable gains. That success can build momentum to try it elsewhere. Let's talk about C++ 17 and C++ 20 features that help with DOD. StudSpan allows safe views over row arrays, enabling cleaner structure of array access. Stud ranges and views can be used to process data in a functional pipeline style. Lambdas help organize behavior in data processing loops. Const expressions and templates can enable compile time layout optimizations. And stud tuple or structured bindings can help group logic while keeping data separate. Modern C++ gives you powerful tools to write expressive, fast and cache-aware code, if you design with the data in mind. Let's wrap this up with some key takeaways. Data-oriented design is about organizing code around how data is used, not how it's modeled conceptually. The CPU cares deeply about memory layout, especially contiguous access patterns. Separating your data, like moving from array of structures to structure of arrays, can yield big performance improvements. C++ is uniquely suited for DOD because it exposes low-level memory control. You don't need to go full DOD everywhere. Start where it matters. Remember, the goal isn't to abandon clean design. It's to align design with performance realities. Thanks for watching, and if you found this helpful, don't forget to like, subscribe and check out the rest of the C++ series.